Differential capacity plots are common in battery research papers such as this one that I previously published. However, developing these plots manually is a time-consuming and error-prone task. Consequently, I developed a program to automate this process and generate higher quality outputs. This video will first show a demonstration of this program, followed by a tutorial on its usage. Beginning with the demonstration, the program is operated via an intuitive graphical user interface. Users begin by clicking button 1 to browse to the files to be analyzed. Several specifications are then provided, which will be explained in the tutorial. After clicking button 6, the program automates Origin to generate a graph as per your specifications. Next, click button 7 in order to open the folder containing the generated outputs. The first of these is a Word file, which contains the image and a caption. Additionally, a PowerPoint file containing the image and caption is generated. Finally, an image file of the graph itself is generated. This concludes the demonstration, so the tutorial will now begin. First, specify the Concise experiment name. This will be used to name the output files and Origin worksheets and graphs. Next, specify the cycles that you wish to plot, with each number separated by a comma. Next, specify the active material mass in milligrams, as this will be used by the program's calculations. Next, use the drop-down to select the manufacturer of your battery cycler. Next, optionally specify your preferred voltage axis title. If this is left blank, a default value will be used. Next, use the drop-down to select your preferred differential capacity units. Next, select your preferred differential capacity axis title or type your own. Next, optionally enter your preferred upper and lower voltage axis limits. If these are left blank, the program will calculate suitable values based on your data. Next, specify your preferred Savitzky-Golay settings. For those unfamiliar with Savitzky-Golay differentiation, the meanings of these terms are explained in depth in the manual and the SciPy documentation. However, the key point to be aware of is that all numerical smoothing methods involve a trade-off between fidelity and noise. Consequently, if we increase the number of sample points, we will generate a more detailed plot. However, this increases the probability of experimental noise being shown. Conversely, if we decrease the number of sample points, this produces a smoother plot with a lower probability of experimental noise appearing, but the plot will have less detail. Through tests on numerous files, I have found that in the great majority of cases, the use of 100 sample points produces plots with a satisfactory balance of noise and fidelity. However, as shown, these parameters are straightforward to modify if necessary. Next, enter your preferred full experiment name. This will determine the caption that will appear in the Word document. Next, specify the Origin template that you wish to use. This affects various properties of the generated graph, such as whether dashed lines are used to represent charging data sets. A detailed demonstration of how to modify this template is given in the link in the description. The Word and PowerPoint templates may also be changed from their default settings using buttons 4 and 5. These templates may also be modified as per your preferences, and again a detailed demonstration of how to do so is given in the video link in the description. This concludes the tutorial. However, it should be noted that the manual contains written forms of these instructions and additional information. Finally, I am offering this program for sale from my website, cyresa.com. If this appears useful to you and you would like to consider purchasing it, then I would greatly appreciate it, as this will enable me to keep making more programs. Thank you for watching, and I hope to help you accelerate your scientific research.